Hello, everyone. Today, we'll change gears a little and talk about heterogeneity, meta bias, and sensitivity analysis. In a few moments, I'll explain to you what each one refers to and how we estimate them and interpret them during the course of our review project. So to just sort of catch us up on where we are, we talked about the fact that there are 9 steps in conducting the meta-analysis. And the seventh step of data synthesis, which is where we are at this point, includes the synthesis of different types of point estimates and confidence intervals, including continuous point estimates as well as dichotomous point estimates, which we expect that by now you would already understand based on the recordings that you've watched. And then the rest of the section of data synthesis talks about different other types of data that we have to synthesize, such as those response, if it's relevant for the purpose of your question, but also for the purpose of today's class, we'll talk about heterogeneity, meta bias, and sensitivity analysis, ways in which it can help us to understand the data that we have synthesized, and make sense of it. So when we talk about publication, about the rest of the analysis steps involved in data synthesis steps, like I just mentioned, first of all, we want to explore publication bias, and we'll do that in a number of ways. Then we'll look at sensitivity analysis and then assess heterogeneity to see if the pooled effect that we have differs by certain specific selected covariates. So let's start with publication bias. The publication bias refers to, the idea that some studies are more likely to be published because of the results of those studies, right? So if you have 200 papers that you have identified in your systematic review from a systematic review search, if publication bias exists, that means that there might be some additional studies out there. It might be another 10, it might be another 20 that never got published, right? Because the results that they found are substantially different from what the field expects to see. So an example of that is vitamin D supplementation. So for instance, in the last couple of years, there have been, maybe not couple, in the last several years, there have been many studies that have been telling us that vitamin D supplements protects against disease X, disease Y, so many different diseases, or that it helps to improve overall health in certain ways, increases certain biomarkers. And, some people suspect that what we might be seeing is publication bias, distorting the scientific knowledge that we are obtaining from vitamin D supplementation studies. Because the idea is that there might be other studies, vitamin D supplementation studies, that are finding negative effects that are not being published, right? And one way that this might bear out is that when you have increasingly large studies, well-powered studies of vitamin D supplementation, for instance, in the context of maybe HIV disease, infertility, if these studies are sufficiently well-powered enough, then they get published because then the editor is more confident that this is a well-done study. And even though its findings are negative, it still gets published, right? But what that means is that some of the studies, maybe because the sample sizes are smaller, that had negative findings, didn't get published, right? So this distortion is what's referred to as publication bias. It leads to a waste in the resources, a lot of the money that goes into studies end up wasting if it doesn't get published, if it doesn't guide us. Because if a negative study is a signal, it tells us to, take a pause and think carefully about your hypothesis. Maybe you're designing your studies wrong. Maybe you're looking at the wrong exposure outcome relationship. But if we don't publish negative studies, then we don't find that out early on. So understanding if publication bias exists can help us to look at the body of evidence in the review. What are we missing, right? What could we be missing? So that's an important context. And the way that we do examine publication bias is 2 ways. We can do it graphically using funnel plots, and we'll talk about what funnel plots mean in a moment, but we can also use statistical methods using the Eggos test. There's also other alternatives. So there's the Beggs test, but the best approach to use is the funnel plot, where you can see where each study is, and I'll show that to you in a moment. So this is what the funnel plot refers to on the left, right? On the x-axis is the point estimate. In this case, for the study is log risk ratio. On the y-axis is the standard error, right? And you have this funnel where the apex of the funnel is typically at 0 here, and the point estimate for the pooled estimate is along this vertical line. So in this study, the pooled estimate would have been negative 0.1 or something along those lines. And then you now have all the studies that went into the meta-analysis on either side of that vertical line, where on either side of the pooled estimate contributing to, those are the ones that determine why we have this pooled estimate here, right? So if you see a funnel plot, how do you interpret it? That's the first thing I want to talk about. So first of all, each dot on the funnel plot refers to one study. So if in this case, there might maybe 10, maybe 15 studies that went into this meta-analysis. And so each dot represents a study, and the x-axis represents the study's results. It's typically on the log scale, right? So the point estimates. The y-axis is the standard error, like I mentioned earlier, which refers to the precision. The closer the study is to the apex, the more precise, right? And if we have symmetry, when you look at the studies on either side, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, if it looks like the studies on either side of the plot, they look kind of well spread out on either side, then there's symmetry, then it means that publication bias is less likely. In this case, we have slightly more studies here, which you might say, okay, because it's odd, but then you also have this one study so far out, so far away from the rest of the studies. And even on this side, on the right side of the plot, you can see that there aren't many studies that are, just spread out, telling us that most of the point estimates, in any case, are bundled up in one direction. And in this case, we can say that there's likely to be publication bias because there is some degree of asymmetry. But if we have a study where the funnel plot looks like this generic funnel plot here, whereas you can see practically all this, there's some degree of symmetry. Most of these dots that you find on the right, you find dots that look fairly similarly placed on the left, right? So that's a symmetrical plot. Now, when we find asymmetry, what does it mean, right? Does it always mean that there's publication bias? That's not necessarily true. Sometimes asymmetry may be due to what is called a small study effect. A small study effect means that the findings that we have from the small study, from a study whose sample size is small, are systematically different from the large ones. And this might be the case when maybe a small study has the opportunity to go in more detail. A small study has the opportunity to go in more detail, use more precise approaches, unlike what you will find with a large study, right? So because of that, an example might be if you're assessing anthropometry, right? With a large study, you might use BMI, which is a rough estimate, or with a small study, you might use something like MRI imaging, in which case you know the exact dimensions, you know how much the body fat percentage is, so the way that you might be assessing with a small study might be different from a large study, and that might be affecting the results that you're finding. The small study might be more accurate, right? So in that case, you would likely have asymmetry for that reason. It might also be because you're using the wrong effect measure in some studies. Some of the studies that you're pulling might be including a relative risk instead of a log relative risk. There might also be other forms of bias. Maybe English language only studies are included in your systematic review. That means that there are maybe Spanish studies that you've not included, or public studies published in China and published in Mandarin that you're not included in your study as a result. That's why you have the asymmetry. So it's just important to understand that this asymmetry exists, and that's why it's important to visualize it and begin to explore what are the reasons why the asymmetry might exist. But certainly in most cases, we think that's due to publication bias. Like I said, we use the funnel plot to assess publication bias. But we can also use the Eggos test to assess publication bias, right? The Eggos test is essentially a statistical test that evaluates whether the funnel plot is symmetrical, right? You get a p-value, and that makes it quite tempting. It essentially regresses, so it's a regression of the effect size of each study against the standard error. So like I said, it takes the data that goes into this funnel plot and plugs it into a mathematical equation, right? Some statisticians argue that the test is not intuitive and discourage its use. There's also some criticism that maybe there are statistical power issues in the use of some of these kinds of tests. And so always present your funnel plot, whether you do present the Eggos test alongside. So I want you to take a moment to look at this funnel plot and decide whether you think this funnel plot is symmetrical or not symmetrical. If you have any questions about it, if you're not sure, please reach out and we can talk about it. Okay. Again, the thing to remember is that symmetry is not, we're not looking for perfect symmetry. If it looks approximately symmetrical, then that might be good enough. If it looks like there are significant differences on the right side versus the left side, then that might be a concern. A few words of caution, it is best to assess publication bias only when there are more than 10 studies, right? Regardless, if you have conducted a study, present the funnel plot and let the reader decide, right? Let the reader decide on what sense they can make of the study. Now let's change gears and talk about heterogeneity. So when we conduct systematic reviews and meta-analysis, it's often the case that we pull studies together that differ in some respects, right? Some of these differences might be in the population characteristics, it might be in the kinds of interventions that have been administered, it might be in the ways that the outcomes were assessed. So maybe, for instance, like in the example that I used earlier, some studies might have assessed anthropometry using BMI, while some other studies might have used maybe better, tools such as maybe MRI, might have used, different sets of tools like calipers to assess skin thickness, all those kind of things. So the ways that each study differs, this then affects the nature of heterogeneity it affects the nature of the findings that we have in the study. So some it might be because of the ways that assessment was done, because of these differences in the study characteristics, might be why we're getting the results that we're getting. This is what we refer to as heterogeneity, right? And when these differences are responsible for the difference in the direction and the magnitude of the estimates that we find from the studies, refer to these as statistical heterogeneity. Remember that we said that you should only consider meta-analysis when the studies are sufficiently homogeneous, right? This is important to reiterate, right? But what we're not saying is that you should only pull studies that look at exactly the same thing. What we're saying is that you have the same exposure outcome relationship. It's meaningful to some degree. Like a reasonable person can say that, yes, certainly this exposure and this outcome that you have assessed in study A are the same exposure and outcome that we assessed in study B. And if that is not the case, then it might not make sense to pull those studies together. So I'll give you an example. If you're interested in physical activity on the risk of infection with HIV, I know I just pulled out that question out of the air, right? So another person then looks at physical activity and the risk of infection with hepatitis B, right? And someone might say, oh, they're both infections, right? But then the other person might say, is that reasonable to pull the outcome of HIV and hepatitis B? That's what we mean by making sure that you're pulling similar exposure outcome relationship. But that's kind of different from if you have 20 studies that have looked at physical activity and HIV risk, right? And in some of those studies were conducted in Africa, while some of those studies were conducted in Asia. Or maybe some of the studies of physical activity had assessed people who use an Apple Watch to examine the degree of physical activity, while some other studies had asked people to just write down, in the last week, how many times did you engage in some form of exercise, right, for leisure. So, that means that in both studies, you're examining different exposures, right? But you're still characterizing them as physical activity. But in the one case, the assessment is more detailed, right? In the other case, you're only looking at the things that people are able to remember. In one case, you might be incorporating leisure, physical activity done for leisure alone, right? In the other case, you might be incorporating all forms of physical activity, right? So you're bringing in different things, and because you're bringing in different things, but because it's still all meaningfully characterized as physical activity, we can say that there is heterogeneity in the assessment of the exposure of physical activity, and that heterogeneity might then affect the findings that we have when we look at physical activity in relation to HIV. Okay? And if the point estimate, so maybe the relative risk or maybe the mean difference that we then have for that relationship of physical activity and HIV are all over the place because of the different ways that you have assessed physical activity, right? We say that there's statistical heterogeneity, and that's the key distinction that we're trying to make from when we say the studies should be sufficiently homogeneous. So how do we test effect heterogeneity in our studies? So first of all, we need to understand that we're really testing, the null hypothesis that we're testing is that the point estimate, the pooled point estimate, the point estimates in each of the studies are the same, right? So this is the point estimate as well as it's equal to the point estimate in study 1, study 2, study 3, study 4, up to study K. And then the alternative hypothesis is that at least one point estimate is different. Okay, so at least zero point estimate of one theta 1 is different from theta 2 or different from theta 3, like that. And there are two ways that we often assess effect heterogeneity statistically, right? We use the Q statistic or we use the I-squared statistic. And if you look at the formulas of both, you realize that what we're really doing is that we estimate the Q statistic and then we use the Q statistic to obtain the I-squared. But the reason why we usually report both is that the I-squared statistic is more intuitive. Okay, but the Q statistic is what's really going on behind the hood. That's the statistical that's the core statistic that drives the I-squared itself too. And with the Q statistic, we can obtain a chi-square test and a p-value, and that p-value we will often then say, oh, this p-value, we can read it off at 0.10. That's the threshold that we're using because the Q statistic is not very well powered, right? When the number of studies are small. So in general, we use 0.10 to read off the Q statistic, the p-value for Q statistic, other than and not 0.05, which is what we would usually use across many other settings. Okay, but for the I-squared, so the I-squared tells us, what's the proportion of the total variability between that we are seeing in the meta-analysis that's due to heterogeneity between the studies. Okay, and we can typically interpret that. We will get a percentage. Okay, so that percentage, depending on where it falls, we might say, oh, maybe there is considerable heterogeneity. We might say there's substantial heterogeneity. So we can interpret it in some way, and it can guide how we sort of think about heterogeneity in our study. And typically, when heterogeneity is considerable, greater than 80%, there is a number of factors that we have to consider. There's a number of things that we have to think about before we conclude the interpretation of our study, including whether we need to throw out the entire study. Okay, so the things that we need to do when there is considerable heterogeneity, first of all, you go back, you check your data, make sure that everything is correct. The other thing you might want to do is just discard the polling. You might just present the individual studies and say a meta-analysis was impossible because the results could be misleading. The other thing you might be able to do is that you explore heterogeneity to understand why the studies are so different. And we'll talk about how we do that in a moment. We typically use meta-regression and prediction intervals. The other thing to think about is sometimes there are some studies that are meaningfully different from the others that you have included. It might be that maybe two studies have used one particular method of assessing physical activity. Maybe in 10 studies, they had asked people to do a recall, right? But in two studies, they had used an Apple Watch. And so when you pull those two studies together, or some form of smartwatch, when you pull the two studies together with the 10 studies, now your results are all over the place. In that case, right, you might decide that maybe if we take out these two studies, right, because they're just so different from the others, then your heterogeneity might be more within a range that makes more sense. So there is some degree of decision making you have to make at this point, but that depends on how you understand the studies that are going into the polling that you're doing. But whatever you do decide, you have to be transparent about it and report. This is what we decided to do, and this is why we decided to do it. So one of the ways that we examine heterogeneity is through meta-regression, like I mentioned earlier. And what we typically do is that we will have a main meta-analysis from all the analysis that we've done, random effects analysis and everything else that we've discussed in the previous class. So assuming the point estimate of interest is the relative risk, right? And so you obtain a meta-analysis where this is your pooled estimate. But in meta-regression, you then want to ask yourself, is it possible that the point estimates from the individual studies, so individual studies in the forest plot, so is it possible that the point estimates from the individual studies can be explained by the study characteristics of those studies? So for instance, is it possible that because some study had more males than more females, could it be that the true relationship, the true exposure outcome relationship in males is different from females, right? Or could it be that the findings you have is because there are more elderly people in your study or there are more young people in your study, and the true exposure outcome relationship in elderly people is different from in young people. So you might be trying to understand this, the way that the individual characteristics of the study might be determining the point estimate that you get, right, in each individual study, which then contribute to your pooled estimate. So you take this pooled estimate and then you using regression methods, you explore whether if you had only males, if you had only females, if you had only people in what age category, and what would your estimate have been, right? And one way to do that is to look at the studies that contributed and you sort of create sub-poolings, so to speak. Like, so among studies where males were less than, where, among studies where you had people who were less than 40, what was the pool, what would the pool estimate be? Among studies where the mean age was between 40 to 65, what would the pool estimate be? So you can then use meta regression to generate a p-value that tells you whether that particular characteristic significantly influences the result. So do the point estimates that you have in the study differ by, do the point estimates that you have in the study differ by the particular characteristic that you're interested in? So the point estimates differ by age, they differ by sex. That's what you're interested in meta regression. And you're able to use a p-value to then say, okay, if the p-value is less than 0.05, just in a traditional way that we explore, that we make inference using p-values, if we think that p-values are relevant to use. But the other way that we can also look at these numbers is the other way that we can also make sense of heterogeneity is to actually generate the prediction interval. So in the first step where we did meta regression, we're only looking at p-values. But in the next step where we have prediction intervals, we're actually generating these numbers. So essentially now, if you look here, in the main study, you have 0.96, the point estimate, but among those who are less than 40, we are able to predict the relative risk among those who are less than 40 and obtain 0.98, but in the older age group, 0.91. We don't have enough studies where the mean age was more than 65. That's why this was not reported. Maybe there was none at all. But if you compare 0.91 and 0.98, you might be able to say, oh, maybe there's not a significant difference. Maybe there's not a meaningful difference, not statistical significance now. Or you might say, well, 0.98 is meaningfully different from 0.91, depending on the context of the study, right? Let's look at in males and females. So here, the relative risk in males is 0.82, which suggests that whatever it is that this is looking at, this is less than 1, where not 1 is null, so it's protective, or it's less likely to occur in males, but in females is 1.11, which means that it's more likely to occur. And that's a qualitatively different, it's different direction of the finding is different. So in males, it's less likely to occur, in females, it's more likely to occur. It's with the prediction interval that we're able to see how this differs. If you just look at the main pooled estimate alone, you will not be able to see this, right? And meta regression would have shown us that 0.049. So typically what we do is that we will start with the meta regression and we'll generate the p-value. We'll see that, oh, the p-value for meta regression is 0.049. And then we might then look at the prediction intervals for that particular characteristic. Alternatively, we can decide that we will generate the p-value for meta regression, but we would also generate the prediction interval for regardless. So that's in this study, we generated both the p-values for meta regression as well as the prediction interval for each of the categories. So whether it's significant or not, it was we report it. So that's another way that we explore heterogeneity. Changing gears a little. So sensitivity analysis. Let's talk about sensitivity analysis. Basically, the methods that we're going to talk about now, they explore different ways that the choice of studies that we include may affect the findings of the meta-analysis. In sensitivity analysis, we take a hard look at the decisions that we made in selecting the methods, and then we ask, how would our results have been different if we have made a different set of decisions? So for instance, if you think about some of the examples that we've used in this class, or the exercise on gastric cancer, you might say, what if we had abstracts that had never become full text papers and we had included them? What if the population had only included studies among the elderly rather than all adults? What if you imputed data in your meta-analysis, and you repeat your meta-analysis under these different states, under these different approaches, and look at how your results would differ from the result that you obtained in your main meta-analysis. So how did the decisions that you made affect the results? And you would explore that by making a new set of decisions, or changing the decisions, and look at how they affect how your results then change. So with sensitivity analysis, there is no set approach. It depends on the questions that you use. But one of the ways that we also look at sensitivity analysis is something called inference analysis. Now, in inference analysis, we want to see whether there might be an individual study or there might be multiple other studies that are driving the pooled analysis findings that we have. Okay, this is often based on a leave one out analysis. Basically, the idea is that you've conducted this meta-analysis, right? You obtain a pooled set of results, so the point estimates and confidence intervals, and then you go back and remove one study, repeat the meta-analysis, look at your results. You go back and remove another study. So you put the first one back, remove another study, you repeat the meta-analysis, look at your results. You take the third one out, repeat the meta-analysis, look at your results, and then look at how your pooled estimates then become, how your pooled estimates change as you go. So let me use an example to motivate this. So if you have this meta-analysis on the left side, right, and you obtain a pooled estimate of 0.38 and confidence intervals of 0.25 to 0.51, right? Now, if you wanted to do inference analysis for all of these questions or all of these studies, right, and you take out study one, right? So if you when you take out study one, you then repeat your meta-analysis and you find a point estimate that's now 0.3681. Yeah, you compare that to what you had, you see that, oh, it didn't really change so much. Or you might compare the p-value, or you might compare the I-squared, right? So maybe the I-squared that you had before was 80%, for instance, and now is 82%. Then you do the same thing, you repeat the study, you repeat the meta-analysis by taking out study two. How does the point estimate change? How do the p-values change? You repeat the same thing by taking out study three. So in sequential order like that, take one out, repeat the meta-analysis, put it back, take another one out. How do your results change? Do your results change meaningfully? So if, for instance, when you took out study three, your point estimate becomes like 0.30, that's a large difference. And that might tell you that maybe study three is really driving your estimates, or maybe the p-values that were significant before now become not significant, or 0.00 becomes 0.1, something like that, 0.2, then that tells you that this study is really driving your estimates, and you should pay attention. So it's important to know if there's a study driving your estimates, because in that case, you don't want to know why that study is driving your estimate. So you go back, you look at that study in detail, understand how that study might be different from the rest of your studies. Maybe it's the sample size that's large, maybe the approach that, that they assess certain things. Essentially, you want to understand what happened in that study. Another type of analysis that we usually do is a cumulative meta-analysis. And the cumulative meta-analysis asks a simple question, right? When people started looking at this question, right? So somebody first conducted a study in 2001, and then the next person conducted another study in 2004, and then 2005, and then 2008, and then 2010, and you have people conducting studies over time, repeating the same study, maybe in different places, and then publishing, right? But what happens over time is that if you went back, assume that every time that someone published a study, you started conducting a meta-analysis. And every time they publish a study, you add it to your meta-analysis, repeat your meta-analysis. They conduct another study, you add it to your meta-analysis, repeat it. At what point does your pool meta-analysis first become significant? That's one. Two is that, is there a time when your estimates become stabilized? That means that they don't start changing all over the place. So let's look at this example. So the labeling of the studies here was alphabetical order. So maybe we can but this is now sorted by year. So the first study was study 8. And when this study was conducted, it was not significant. Yeah. And then the next study that was conducted was study 12. And then when this study was conducted, when you add the study 12 and study 8, you get a significant estimate. Yeah. When you add study 7 to it, it now no longer becomes significant. Maybe because study 7 was very negative study, something like that. But when you add study 9, it becomes significant again. But what you notice now is that as you add more studies, it no longer changes all over the place. The effect estimates begin to stabilize. And by the time you get to this study, you have an effect estimate that essentially doesn't change anymore. It's 0.36, 0.37, 0.38, but those are not meaningful differences. So these are the kind of things that you want to understand by when we say that we're conducting cumulative meta-analysis. We want to understand if there are first study effects. So sometimes first study effects happen when somebody conducts a study and finds one set of estimates, and as a result, other people who then conduct that study, they look at that exposure outcome relationship, then start finding the same ballpark estimates. Or so that might tell you if you find first study effects and there is also publication bias, it might tell you that the other people who were not finding estimates that were similar to the first study, yeah, were just not publishing because, or maybe they were not able to publish because nobody believed their results. So that's what we mean by first study effect. So essentially what you do is that you take together all of these analyses and make sense of them and use them to guide the extent to which you believe the findings of your meta-analysis. So what are the key takeaways from this class? First of all, we talked about publication bias. We said publication bias is really critical and it helps us decide whether there might have been studies that should have been published but never did get published. And we talked about the ways in which we assess publication bias with funnel plots. That's the most important takeaway from today's class. We then also look at heterogeneity and how statistical heterogeneity occurs, and why it's important to explore because it will help us understand the data in more detail, when we should absolutely change our strategy if there's considerable heterogeneity. We talked about that. We also then talked about sensitivity analysis, in the context of like inference analysis, cumulative analysis, and how we should tie all the findings across all of this together to make our inference on what we think that the findings of this meta-analysis mean. Thank you very much.